Okay, so now we've got our stiffness matrix, and I made a correction here. This was actually 200 instead of 100. The previous video showed a 100 there, but it should be 200. So we'll continue with the 200, the correct value, as we finish this problem. Okay, so now what we want to do, we want to start plugging in values into our system of linear equations. So we know that F1 will be some value, because remember we're at a fixed end support and there will be a support reaction. F2, if you look back, we have the 20 kilonewton applied force, so in the positive direction, and F3 was 0, and F4 will be another support reaction. And this equals our stiffness matrix times our displacement vector. So just before I move on, I just want to point something out for you guys to clarify a property of the stiffness matrix. You can see this large one is nothing but just the addition of our, remember our first K1 is that stiffness matrix minus is that stiffness matrix, and then we can look and see our K2 is this, our second element stiffness matrix, 100, and then finally our third. So if you remember, K3 was 200, K2 was 100, and K1 was 100. So that's just basically how you want to orient these matrices in a diagonal formation. And as I said before, when we're summing up our matrix, the overlapping rows and columns, you just simply add them together. So this is how we get the stiffness matrix in our calculations. And now we know that U1, 0 fixed support, U4, 0 fixed support, and U2 unknown, U3 unknown. Okay, so now what we need to do is calculate U2 and U3. Now by doing so, we can rearrange this matrix, because see, we have in our vector, our displacement vector, we have a 0 component in the first slot, and then also in the fourth component is another 0 component. So if you know matrix multiplication, having a 0 component in your matrix multiplication, that is actually going to cancel out this entire first row. Because if you go carry through the matrix multiplication, the first component is times by the entire first column, the entire first column, and being 0, it's going to cancel out every value and it's going to be equal to 0. Similarly, we have our fourth row on our vector to be 0 as well. So now we can cancel out and cross out the entire fourth column of our stiffness matrix, because it's all going to be 0 anyways. And because we want a square matrix, we can actually cross out the entire first row now, and also the entire fourth row, and this will make it square. And this is a property of the matrices, such that we can actually still solve for the unknown components and reduce it down to a 2 by 2 matrix, or however many zeros you have, you can reduce it down to a 3 by 3 or a 2 by 2 or whatever. So now we can rewrite this, and now we see that we just have 2 unknowns and 2 equations. So if we use our matrix, I'm going to use Gaussian elimination to solve this matrix. So row 1 plus 2 times row 2, so I'm going to cancel out the first component. So this says so U3 is equal to 0.04, and then now remember, I'm using U3 and U2 here because we've canceled out the first and the last rows and columns of our larger matrix. So now we're just looking at U2 and U3. So that's why we have U3 here. U3 is equals 0.04, and then U2. So we can say that 100. Therefore, U2 so now we've solved for our nodal displacements U3 and U4. So now let's plug everything back into our big matrix up here that we've solved for. Okay, so now looking back at our matrix that we crossed out our rows and columns for, we can actually plug in our values for U1 and U2. Sorry, for U2 and U3. So U2 was 0.12 and U3 was 0.04. So now we have a system of equations and we just have our unknowns at F1 and F4. So in order to solve for these, all we have to do is matrix multiplication. F1 is equal to, if you remember linear algebra, it'd be our first row times our displacement vector, and that's all we have to do to find our force. See, it's simple. So F1 negative 12 kilonewtons. And then similarly F2, we just take our not F2, we want F4. So same thing with F4, we take our fourth row and multiply it by our displacement vector again. So F4 is equal to negative 8 kilonewtons. And there we are. We have our both of our support reactions, F1 and F4. Okay, so look, what do we need? Find displacement at the nodes. We've done that. We've found U1 equals 0, U2 equals 0. I don't remember what U2 was. 0.12, U3 equals 0.04, and U4 equals 0. Done. Support reactions, F1 equals negative 12. Okay, that makes sense because we're going in the negative direction because we have a force pushing us right. And F4 is equal to positive or negative 8. We have negative, I believe, yes. Negative 8. Negative 8. And that makes sense because our 20 is going to the right, and therefore our reactions should all be going left. Okay, so that makes sense. And there you have it. We just solved the support reactions, our nodal displacements, using the stiffness matrix. So if you like my video, please like and share, subscribe to my channel, and visit my website at www.everythingeng.com. Thanks for watching.